There are several versions of simultaneous iteration, and today we're going to study the unnormalized simultaneous iteration and in particular its convergence. This is the unnormalized simultaneous iteration. The convergence of this algorithm is in general quite complicated, and we're going to start by showing the convergence under simplified conditions. So we're going to assume these things. So in particular, we're going to assume that A is diagonal and that the eigenvalues or the diagonal elements of the A matrix, they are ordered and they are distinct in modulus. We're also going to assume that the initial matrix, so it will be a square matrix, is a lower triangular matrix with ones on the diagonal. And later we're going to see that we can reduce the general case almost always to this case. So let's first try to understand it. So we want to show that the Q matrix in the unnormalized simultaneous iteration is will approach the eigenvectors of the matrix A. And in fact, in this case, the eigenvectors are just the unit vectors. And before we dive into the theory, we need to establish results which is general for QR factorizations. So we assume that QR is a QR factorization of A, and so this is a general property of a QR factorization of A. Okay, so by just looking at the first column of this QR factorization, okay, and now we're going to see that for the second column we have an identity that will turn out to be useful later. So we're going to show that that Q2 R2 is equal to, okay, so it's almost equal to A2, but multiplied by this matrix, sometimes called the spectral projector, containing the vector Q1. So Q2 R2 is essentially equal to A2, but with this multiplication. Let's prove this. So column 1 is just exactly implies the equation 1. Okay, and if we now take the second column of this star equation and multiply that by this spectral projector, okay, so the left-hand side here is just, because it's a triangular matrix, we just get two terms involving Q1 and Q2, and okay, and that's just the right-hand side multiplied with this. And the reason we are doing this here is because this multiplication with this will eliminate Q1, so we'll only get Q2. So a property of the spectral projector is that if you multiply it by the Q1 vector, you get 0. And if you multiply it by another vector in the Q matrix, you just get the Q vector. And so if we just use that identity here, we get directly this equality up here. And then this can be continued for the next step. Okay, so we want to study the convergence of the normalized simultaneous iteration. This is just the iteration in this setting where lambda is a diagonal matrix. And let's look at this equation one column at a time. So let's first look at the first column. Okay, so the column 1 just reduces to that we have a essentially that the first column of Q times some scalar is equal to lambda to the power of K times the first column of this V matrix. And do we want to study like the convergence of the first column here? So let's look at this column and use that it's normalized, so we can divide by itself. And in order to get this expression here, we also extend the numerator and denominator with R11. Okay, and now we can directly insert this expression here in the numerator and the denominator. And we observe here that this is exactly the power method applied to the lambda matrix started with this vector here. So we know exactly what the convergence is from before. Okay, that was column 1. Let's now look at column 2. And when we use column 2, we're directly going to use also the proposition. Okay, so we have eliminated Q1 from the left-hand side here in the QR factorization, so we just get essentially Q2 times the scalar is, the spectral projector times lambda to the power of K. And recall that we started our method with V matrix, which is a lower triangular matrix with ones on the diagonal. So this matrix actually, this vector actually looks like this. So V2 has a 0 on the top, and that means that when we multiply this with a diagonal matrix, normally we would have a lambda 1 here, but since we only multiply it by 0, we might as well remove it. And so here we have a matrix to the power of K, where we replaced, which is a lambda matrix, except that we replaced lambda 1 with 0. And we call this lambda minus to the power of K. Okay, now let's look at this expression a little bit, and we take this term, the last term, and use that we already know that the Q1 converges to E1 with a speed or an error determined by this delta 1k. And so here we have E1 and some error term, and when we multiply that into this equation here, which has a 0 on the top here, this term disappears. So we only get an O of delta 1 in this part. So we can replace this whole thing with identity plus O delta 1k. Okay, and now we're going to similarly use that this is something like the power method. And so this is equal to the power method up to some scaling. So let's let's normalize it and multiply out the normalization. Okay, so we see here that this term here, when we multiply it out, we get is exactly the power method applied to this lambda minus matrix. And the largest eigenvalue of this matrix is lambda 2. So we get E2 is the eigenvector plus some error term, which is determined by the quotient of the two largest eigenvalues. So we get E2 plus delta 2k where we have this quotient. And now we just have to multiply this out. The final step consists of removing this term here in the same way we had before. So we're going to take Q2 and use that is normalized and use this expression. So we just used the complicated formula we just derived, which essentially that the Q2 times R22 is E2 plus these error terms. And so we insert that in the numerator and denominator, and that's a scalar term, so this cancels. So here we have E2 plus some error term, that goes to 0 divided by, well, normalization, so E2 plus some error term. And so this approaches here E2 with the same speed as this here. And so here we've shown that Q2 approaches E2 with the speed determined by these quotients. And now you can continue this with Q2, Q3, and Q4, and so on. And by this we have shown that the Q matrix approach this identity, these unit vectors, which are the eigenvectors of our original matrix.